One of the greatest threats in human health is those things that are not visible to the human eye. Example of this is ionizing radiation. Hear, smell, see, taste, touch. All of the five senses cannot detect radiation. One of the greatest challenges of science and technology is to create a device that can detect, prevent, or reverse the potential effect of radiological and nuclear material to its environment. There are many kinds of radioactive sensors, and an example of this is the Geiger counter, or also known as the Geiger-Müller tube. This was invented by German physicist Hans Wilhelm Geiger at 1908 and was perfected 20 years later after by his student Walter Müller. The design of a typical Geiger counter consists of a metal tube, the GM tube, with a glass or mica window at one end. This is where radiation particles enter. A metal wire that has a strong positive charge is placed in the center of the tube. The sealed tube is filled at low pressure with an inert gas. What is radiation? Radiation is an energy traveling in the form of particles or waves in bundles of energy called photons. Beyond the ultraviolet radiation from the sun is a higher level of radiation, and collectively it is called ionizing radiation, which can cause damage to matter. There are different types of radiation dosage, and the SI unit used to measure radiation is called sievert. It can range from 1 to 1000 millisievert depending on the sources of the radiation. There are different types of radiation, alpha, beta, and gamma. They differ in their ionization ability and how penetrating it is. The image shows the health risk of these different types of radiation.
Hey everyone, I am Ira Gabriel Felipe and we will discuss about radiation sensors. There are two types of radiation sensors. First is the scintillation detector and second is the gas filter detector. First we will discuss about the scintillation detector. The basic principle behind this instrument is the use of a special material which glows or scintillates when the radiation interacts with it. The most common type of material is a type of salt called sodium iodide. The light produced from the scintillation process is reflected through a clear window where it will interact with a device called the photomultiplier tube. The first part of the photomultiplier tube is made of another special material called a photocathode. The photocathode produces electrons when light strikes its surface. These electrons are then pulled towards a series of plates called diodes through the application of a positive high voltage. When electrons from the photocathode hit the first diode, several electrons are produced for each initial electron hitting its surface. This bunch of electrons is then pulled towards the next diode where more electron multiplication occurs. The sequence will continue until the last diode is reached. This is where the electron pulse is now millions of times larger than it was at the beginning of the tube. At this point, the electrons are collected by an anode at the end of the tube, forming an electronic pulse. The pulse is then detected and displayed by the instrument. Next, for the gas field detector. This instrument works on the principle that as radiation passes through the air or a specific gas, ionization of the molecules in the air occur. When a high voltage is placed between two areas of the gas-filled space, the positive ions will be attracted to the negative side of the detector, or also called the cathode, and the free electrons will travel to the positive side, the anode. These charges are collected by the anode and cathode, which then form a very small current in the wires going to the detector. By placing a very sensitive current measuring device between the wires from the cathode and anode, the small current is measured and displayed as a signal. The more radiation which enters the chamber, the more current is displayed by the instrument. Many types of gas field detectors exist, but the two most common are the ion chamber used for measuring large amounts of radiation and the Geiger-Müller or the GM detector used to measure very small amounts of radiation. There you have the two basic operations of the two types of radiation sensors.
The applications for radiation sensors are widely used in the field of medicine, industrial, and space programs. First, in the field of medicine. Medical practitioners, especially those who are involved in radiology, nuclear medicine, and radiation oncology, have personal radiation sensors to make sure that the radiation around their workplace is safe. Some radiation sensors, like personal dosimeter, can be carried even in their polo pocket, strapping at belt or tied at the forearm. So here is an example of a pocket dosimeter, a belt dosimeter, and a forearm dosimeter. Lastly, space programs use radiation sensors for monitoring levels of radiation in reactor power systems, which use controlled fission, radioisotope power systems, which utilize the heat produced by radioactive decay, and environmental heaters, which provide heating to surrounding equipment on interplanetary spacecraft.
Who are working at nuclear power plant industries usually use radiation sensors for monitoring, analyzing, and preventive measures in order to avoid radiation leak or worse, a nuclear meltdown. They are using these sensors also to detect the radiation level in water, which is used to cool the reactor before releasing to the environment. On the other hand, people working in the mining industries use radiation sensors in the science of radiographic X-ray for finding imperceptible corrosion in metals. Safe operation of vehicles and machinery is an operational imperative for the mining industry. Equipment failure can be extremely costly on many different levels, and non-destructive testing is a crucial tool for the industry, helping to minimize the potential for failure by the continuous monitoring of the health of plant and machinery. Machinery and equipment on a mine site is often under sustained operational stress due to the weight of the material being moved, and non-destructive testing methods play an important role in keeping equipment operating optimally, minimizing unexpected downtime, minimizing production losses, enabling operators to plan repairs or implement predictive maintenance programs. Radiographic testing is a valuable non-destructive testing method that is widely used to examine plant and equipment and keep it operational, a crucial factor in ensuring the ongoing safety and profitability of mining operations. People who are working at nuclear power plant industries usually use radiation sensors for monitoring, analyzing, and preventive measures in order to avoid radiation leak or worse, a nuclear meltdown. They are using these sensors also to detect the radiation level in water, which is used to cool the reactor before releasing to the environment. On the other hand, people working in the mining industries use radiation sensors in the science of radiographic X-ray for finding imperceptible corrosion in metals. The ongoing safe operation of vehicles and machinery is an operational imperative for the mining industry. Equipment failure can be extremely costly on many different levels, and non-destructive testing is a crucial tool for the industry, helping to minimize the potential for failure by the continuous monitoring of the health of plant and machinery. Machinery and equipment on a mine site is often under sustained operational stress due to the weight of the material being moved, and non-destructive testing methods play an important role in number 1, keeping equipment operating optimally, 2, minimizing unexpected downtime, 3, minimizing production losses, and 4, enabling operators to plan repairs or implement predictive maintenance programs. Radiographic testing is a valuable non-destructive testing method that is widely used to examine plant and equipment and keep it operational, a crucial factor in ensuring the ongoing safety and profitability of mining operations.